Fine. Today, we are going to complete the theory. After that, I said we are discussing the questions. First of all, just like second part theory of elasticity, then Hooke's law. First you write Hooke's law. Hooke's law is actually said by him long ago in a different way, because when a wire is loaded, straight line is there, then after that slight curve was there. Then elastic limit, this is the proportional limit. Early they used to say up to proportional, not a proportional limit, up to elastic limit. Now we consider only the straight line is up to this, no? So then it is correct within the proportional limit. Proportional limit. So then how to say that? This is force, this is extension. Then within the proportional limit, extension is directly proportional to the applied force. That is what we have to consider there as Hooke's law. Right, first you write within the proportional limit, a force applied to a suspended wire is directly proportional to the extension. F is directly proportional to extension. F is equal to KE. K is proportionality constant. K is proportionality constant. Then, now this proportionality constant is called force constant. This is called force constant. Right. Then write F is directly proportional to E, F is KE, K is proportionality constant. And it is given the name force constant. Actually, K is force constant. Force constant. Now, Hooke's law can be told in another way. That is, I said, within the proportional limit. Another way, when the proportional limit is not exceeded, it is not jumped from the proportional limit. Then the same thing. Then write another way, when the proportional limit is not exceeded, proportionality limit is not exceeded, the applied force on a wire is directly proportional to the extension of the wire. That's another way they normally say. Now, Hooke's law is concerned, this equation is needed for that. Normally in mechanics, most of the time we are using rather than in properties of matter. But there's another way. This can be applied even for a suspended helical spring. So then there is a force X. Right. Then right. Hooke's law is correct even for suspended helical spring. Therefore, again F is directly proportional to E. F equals KE. But this time we don't call force constant. We call it spring constant. We call it spring constant. Just draw this graph. And there is another thing I had to remember. You have to remember that Young modulus equation can be used when a force is given to a rod like that. Then it is compression. So then Young modulus is equal to compressive, pressive, then stress divided by compressive strain. You can write like that. Early we wrote tensile and here also tensile, stress and strain. Stress and strain. Tensile means linear. This is not linear, this is compressional values. So, compressive, when you consider compressive stress, that means compressive stress, compressive force divided by cross-sectional area. That means if the rod is there, the applied force is this, cross-sectional area is this. Then compressive strain, compressive strain is equal to compression divided by initial length. Compression divided by initial length. Units and dimensions are the same. Nothing would happen with this. No dimension, no dimensions, no units. Here, dimension ml -1 T -2. Dimensions of pressure. SI units, Newton per square meter or Pascal. And remember, any animal, even including ourselves, is concerned, our weight is always on the legs. So therefore, compression is there for the legs. And when you are standing on one hand vertically like that, that is also compression. There we consider about the bones are concerned, or they give the bones saying that it is cylindrical and there is a cavity. Then when there is a cavity inside for anything, area is concerned only the area without the cavity. This is the area only. Area. Right. Example. Find the maximum load which may be placed on a steel wire of diameter 0.1 centimeter if the permitted strain must not exceed 1/1000 and Young modulus for steel is 2 into 10 to the power 11 Nm minus 2. Here actually I gave the question just to show you how to write the equation. So Young modulus, this is considered as wire that is normally stress divided by strain. So then when the wire is getting the maximum strain means it has exceeded to the maximum length. Then right, when the maximum strain is there for wire gets the maximum extension. When the maximum extension there, in order to get that, the force must be maximum. Force must be maximum. Then stress becomes maximum. Then the stress becomes maximum. This argument you have to understand. Strain is maximum means strain max. That means maximum extension divided by then initial length. This is maximum. Then this is maximum. To get the maximum extension, see, then according to Hooke's law, the force is maximum. This is the maximum place, F max here. Then the force is maximum, then stress. Those are tensile. Stress is equal to maximum force divided by area. So therefore, Young modulus equation can be altered as maximum stress divided by maximum strain when either strain is maximum or stress is maximum. In other words, extension is maximum, force is maximum, same way you can write. That is the reason I explained it. When compression is concerned, we'll say there is a certain composite rod. It consists of just like a red cuboid, or it consists of after that another cylindrical part like this cylinder, maybe another kind of again cylinder, or some more objects can be connected, but there is a common axis. Common axis. So then force along the common axis everywhere the same. Everywhere the same. Then note it down. That means here also F, here also F, here also F. If you want to find the total extension for the first part, find the extension considering the force is F. Second part, find the extension separately. E1, E2, and for this also separately. Total compression is then, or extension. If the forces are outwards, extension, inwards, then that is compression. Next one briefly. Elastic fatigue. And energy stored. We'll say there is a wire, metal wire. Normally, for a wire, it is suspended. You are giving certain force. Then within the proportional limit or up to elastic limit, we'll see. And you release the force. Again, you do it. Like that, you repeat for so much of time. That means several times. Then what happens is, when it is stretching, the force is applied, the wire stretches. During the stretching, energy is stored in the wire. Previous section we considered. Now the force is taken off. Then what happened? No force is there. Then that energy should be given out. Automatically energy comes out. Actually can't come out. What happens is heat generates in the wire to remove the energy. Therefore, the temperature of the wire goes up or increases. Then, if you want to, we'll say, normally wire is to be cut and we are using a plier or wire cutter. But if you do not have, what you do is, we bend so many times. I'll explain that part before the theme. Then the theory related to that is, when the load is given and taken away, again given several times, I said, then it does not come back to the original length. It does not come. that means the force is given, an extension is there at different due to different forces. When those values are being taken off, the extension is not the same as when the wire was loaded. That means applying the force. Finally, it does not obey the Hooke's law. That situation is called elastic fatigue. Elastic fatigue. So then when you want to break a wire into two pieces, you can bend, release, bend, release, bend, again release. Then what happens if that particular part comes to elastic fatigue? Finally, it breaks with a small force also. When it comes to the fatigue, maximum value is not needed. So less force is enough to break the wire into two parts. So therefore, elastic fatigue is really good for certain situations. There is another next one you write, elastic hysteresis. Hysteresis. Elastic hysteresis. Then you have to understand what it is. Now, if you do a certain experiment, loading and unloading the wire even within the elastic limit or proportional limit. So then, and we plot a graph. We are plotting a graph. That graph is force versus extension. Force is here, then extension is here. Then normally, even up to the particular point, it breaks. This happens actually with the fatigue also. It's like that. Not straight line is coming in that way. When this is loading, unloading is concerned, it is not having the same extension, less value. So therefore, this comes like it's not taking the same path. This is unloading. Loading energy is absorbed. Unloading releases. Temperature increases. Then certain energy lost. Right? Where are you getting? This is a called hysteric loop. And energy for loading, when it is loading the energy, we'll consider that first. Loading one, we'll consider in green, the area under the curve roughly. So this is the energy stored in the wire when it was loaded. Unloaded, this is the amount of energy there. Then we can say this is the extra energy. And it converts into heat. This is the amount where the area of the hysteric loop is the heat energy produced. Just draw it. I'm just explaining now day-to-day life how elasticity is used. We'll consider one by one. In details, it's not needed. The heading is needed or the idea is needed. When you consider rubber gloves, stretching, we stretch it and put into the hand or your fingers. The other rubber is used. Then, right, in rubber gloves, stretching occurs due to elasticity. In garments, garments means dresses. Normally, elastic is used. There is no need to explain. You know that elastic is used for garments. When using the elastic, the length is less. When you wear, the length increases. You wear the elastic. There is a particular belt like that, belt or strip, that is called elastic. People say elastic. We are using elastic for the garments. But when you are wearing for months, stretching for a longer period, we are going there. After that, when you remove that, again comes to the almost original length. But every day when you are several times when you are wearing, every day, maybe every day, then stretching, again releasing the load. Actually, load means we stretch and wear. After that, it has come to the fatigue. After that, it does not come up back to where? Originally. Then it does not get stuck with the body. So you have to use a new elastic or replace that by else. So then if they ask about garments when you are using elastic, why it loses later due to elastic fatigue. Then right, in garments, elastic is used when the garment is worn several times for months, the elastic comes to fatigue. Then it does not come back to original length. That is due to the fatigue, elastic fatigue. Even socks are concerned. Socks, the upper part of the socks, small rubber coats are there. When you wear for a longer period, fatigue. After that, it is not getting stuck to your leg. Right. Day-to-day life. Another one, cushions, rubber cushions, then write rubber cushions, they are actually not the tensile stress or strain. That part is not in the syllabus, but I'll just touch only later. Then, but even cushions, rubber mattresses, everywhere you get the elasticity. Here, we'll say rubber mattress. When you sleep for 2-3 years, what happened? Initially, when you buy it, the thickness is maybe 12 centimeters, 14 centimeters, like that. Thickness increases, price also increases. So after that, now when you sleep for a longer period, if a person is having 45 kilos, like that, force is less. But large body is concerned, will say myself like that, or fatter, very fat person sleeps, what happened? Force is large, compresses. Again, when he gets up, goes up. But anyhow, quickly, within a very short period, it comes to the fatigues. After that, the mattress does not come to the original length. That is not comfortable after that. Then, right? So when we consider mattresses, due to the force when you are sleeping, the rubber compresses. After the long period of usage, or long period, when it is used for longer period, the rubber comes to the fatigue level. After that, it does not come to the original thickness. Even the person is not sleeping on it. Basically, then the mattress is not comfortable. Even this is plastic, the clip, this is not actually elastic limit, plastic, but it also within the plastic limit like that, it comes back up to a certain extent. So therefore, plastic also extends. So then this clip, when I put it inside, it expands. But when I take it out, again it contracts. No force. The force is outwards here because force is given from this part. But after long use like that, same, then it loses. It falls because it has come to the fatigue again. Right? There are a lot of situations where the fatigue is applied. Right. Now I'll come to another situation that is concrete. Then here plastic now not needed to say. Now consider concrete. Concrete. You have to understand what is concrete. It's a mixture of normal cement layer is mixture of sand and cement. Cement portion ratio is more, then strength is more. For normal cement mixed with sand, normally we call mortar. So this wall and all are plastered, we use in that. Even the bricks laid using that. normally 1 to 5 cement sand. You have to understand few things. Cement sand ratio is this. This is normally used to lay bricks. There is no need to remember the values. Lay bricks means you are making the wall like that. But when you want to plaster, plaster means covering the wall with another layer. Either this or 1 to 6 is used. But this is not stronger than like that. If you use 1:5, then it is very strong. Sometimes you can drive a nail inside. It bends. Even a concrete nail jumps off. Right? Then that is called normal cement. The cement is laid on the floor. Then also they are using 1 to 5. One cement. Concrete is different. There you get small stones. Those are called metals. Right? Then cement is there. Then sand is there. Cement, sand. Sand, then cement, powder like this. Normally, for concrete, 1, 2, 3. That means not according to mass volume. We'll say 1 bucket of cement as a volume. Same bucket you get 2 buckets of sand and 3 buckets of metals. Metal means small stones. Normally, those are sometimes called 3x4 stones. But concrete mixture, there is another one. 1, 2, 4. The 1, 2, 3 is concerned, after putting the concrete, it is very smooth like that. Here, after putting that, you can see the stones like this. That is a difference. This is also strong. But both are concerned, normally concrete, the cement is getting hard. To come to the, these are all mixed with water, plus water. After that, minimum of 14 days, it takes concrete to settle. But to get the best one, it is 21 days. Normally, concrete slabs are placed on the first floor, second floor like that. The supports are there like that. These are removed after, should be removed after, not should be, before 21 days it should not be done. But I have seen there are situations, they removed 1 or 2, keeping 1 or 2 supports within 14. But normally 21 days it takes. Right. Now it's strong. But this concrete is just the mixture of, as I said, metals, sand and cement. Now there is a block like that, or slab. Small slab over the drains like that we put. If you give a force on this actually start to compress. Then compress and cracks. It cracks. So on the surface you can see like that. Sometimes hair lines can be seen. Hair lines means the lines are very tiny, just like hair. So that means this concrete is not strong. Concrete slab is not strong to bear up larger forces. Then to get rid of this problem, another thing is done. That is, before putting the concrete, we are or we can use wire grid. Then first you lay a small layer of concrete, then you place this wire layer on that, again put concrete. These are called normally reinforced concrete. Then right, normal concrete is not strong that much. Therefore, when putting a slab, wire rods or iron rods, sorry, iron rods are used as shown in the diagram. This is called reinforcing. REINFORCECING, reinforcing. Or reinforcement is done. To get a very strong slab, the diameter of the rod must be greater, larger. Why? Basically, we can't apply directly this one, F over A, E over L for this. There are different equations, but even you consider like that, larger one, A is larger. Then the stress is becoming less on the concrete. E is less, L is the constant value. So then it is even for the good concrete slab, you have to use. Normally they are using 10 millimeter diameter iron rods. 10 millimeter. If you want to have a very strong one, then you are using 12 millimeters. You have seen that below the slab, there are some large rectangular shaped ones. Those are called beams. So beams are concerned, you get larger. So normally 4 rods are there, basically. But it is the 6 rods are there, laid like that. And it is just like a box. They are connecting. So then these wires can be sagged down. So therefore, we connect again another square type or rectangular type loops. So within this loop, we are sending and connecting. That is for the slab. Below that, you get beam. Building is large. This slab thickness must be larger. Large 18 millimeter normally rods are used. And we get the question directly for the pillars. Normally concrete is used as pillar and slab is put, definitely this cracks. You have to have 4 rods vertically. Those 4 rods again connected with this kind of loop. So building is large, huge, normal we'll say 2-story building. This diameter is 10 millimeter diameter is enough. But 3-4 floors are there. This rod must be 12 millimeters. More than that, it should be 10, 18 millimeter or 24 millimeters. Very thick. But not only 4, there are 6, 8 like that. Well, at the side, Colombo apartments are there. No? The other side is concerned, there are large buildings. Those are called skyscrapers. Skyscrapers. Scrape the sky. Then a 5-story building like that, their columns are mostly used like this, not square. It's just like a book, the shape of this, not the square. So then reinforcement is done here. Like that. So then you can understand what it is. Then like reinforcement is done for the concrete in order to get the strength. In order to get the strength. There is another type of concrete, pre-stressed concrete. Pre-stressed. Pre means early. Stressed. There, what you do is, before putting the concrete, we'll say iron bars are there. Those are given a force and stretch outwards. So, stretch towards, given a force, and stretch now. The original length is up to this. Now this is the extension. Then we put the concrete. After 21 days, force is replaced or removed. Sorry, not replaced, removed. Then the rods are trying to come to the original length. Can't come. But it is very strong. Normally, most of the students can see stressed concrete, pre-stressed concrete as sleepers on the railway track. Sleepers, the cross concrete are there. Those are pre-stressed ones. Now, basically why I said it, because you can't say in our physics paper, when the concrete column is there, they explain about what I explained, they will explain in the text. Those are called comprehension questions. Physics normally you get now 3-4 questions like that, not like those days. So therefore, sometimes you can't understand what they say from that small passage or the paragraphs. That is the reason I explain all those. But we can't say this is not in the syllabus directly. Users, they say. But you can't argue, no, it is out of the syllabus because they explain and ask the question. Those are not out of the syllabus. Right? You understood now? Okay, so then pre-stressed concrete is very. Now I'll just explain what's happening when a force is given to a block like that. We'll say this is a rubber cuboid, not a cube. Now we want to build a sponge like that. We can't apply force or it will break that part. So therefore what we do is tiny strong plate. We'll say tiny board is pasted onto that. And we apply the force onto this. then what happens is volume changes directly. And volume changes as well as area also changes. When you apply the force, area changes. Anyhow, force divided by area we can consider for this. Force divided by area. That is the total volume we consider. Then after that, there is another thing, that is volume. So then if it is volume what happens? If it is compressed, volume reduces. If it is expanded or extended, then volume increases. Basically, if you consider certain volume and force is given inwards like this, then volume decreases. Volume decreases. Decreased volume means concern the decrease amount, the volume is minus delta V. Minus is for decrement or decreasing that. And here force divided by area there. Delta V divided by V. This is volume strain. Volume strain. Minus signs because it compresses. If the force outwards, plus delta V. Then force divided by area is the other one. That is volume stress. Volume stress, you can say bulk. You can say bulk. Hello. Hello. Okay. Apa tadi ni? Oh. Memang. Pada anda ni pada nanti. Pada tu nanti ni. Ini masih kita ni apa? Produk tu peno, kita ni nanti ni peno makar tu na. Makar tu ni atau ni. පන්සල වාරේ දකුණු පැත්තේ පළවෙනි ගේට්ටුව පරණ ගේට්ටුවක් තියෙනවා එතනින් ඇතුළට. හරි. Now then volume reduces if the force is outwards, it increases. Then what happens? That increases, this is plus delta V. If you want, you can write plus. Anyhow, volume is bulk. Then we can say for volume elasticity, bulk modulus. For that, we say modulus is bulk. Understood? That is called bulk modulus. Then we have to find the strain and stress. Strain is concerned, that is for the bulk one I mean, then you are getting bulk stress, bulk strain. That is equal to bulk stress divided by bulk strain. Right? Just note down this. Bulk is volume. Here you might think that why I explained it. The modulus, this bulk modulus is needed in unit 3 for the sound. There, can you remember? Longitudinal velocity of sound is equal to E over rho. Even AI is concerned, bulk elasticity E over rho. Square rule. Then this is the bulk modulus. Even it is not there in the properties of matter, they give the bulk modulus for that in order to find it. Then bulk modulus for a gas, this is third unit, not here, is gamma p. So therefore this equation can be written as gamma p over rho square root. P is the pressure of the gas, normal air, atmospheric pressure. Gamma is ratio between the two principal heat capacities. That is called Cp over Cv. Those are for the, this is in heat, that is taken, E is taken from this one, and longitudinal velocity. You have done this, most of the students. When you come to properties of matter, this is done. So that is the reason that's needed. For a gas, if you apply it, it is different. Why? A gas is concerned force divided by area divided by volume decreases delta initial pressure. Then delta V over V reduces minus V is equal to bulk modulus. Bulk modulus, capital E or capital K. It is denoted by. F over A is, what is F over A? That is pressure. So then now you get the pressure there. Actually, what happened is increase in the pressure. This is delta P over minus delta V over V. This is not under this section, that is in future. That is the reason I just explained that. Force is given, there is an increase in the force, that is considered there as the increased pressure. For area also we can do it, but area modulus is not taken that much. Now this is the end of the theory of the second part. Then we have to do the questions.